webinar series. In today's session, we will discuss the steel structures further in continuity to your previous webinar, where we discussed a shed type building. Typical industrial building or a shed type building was discussed. In today's session, we will discuss buildings or multi-story buildings. So let me take you through these slides first, and then we will indulge in the ETABS to discuss various other things that are part of your analysis and design. So ETABS for steel buildings, it's a good choice. It is a very well streamlined software. It has an integrated approach. That means starting from modeling, analysis, design, and even detailing, you have a complete package can help you in your design office requirement of steel building analysis and design. And the modeling is the key, and it is done through object-based modeling, which simplifies the finite element work that is required for the structural analysis. And then it is optimized for the buildings, like various automated features that will help you in the modeling, loading, assignments, reviewing of the results, etc. So ETABS will be a great choice for a steel building analysis and design. In this particular webinar, we are focusing those who are new to this program, as well as who have experience in ETABS, most likely with RCC buildings. They will also be benefited from this webinar. So we have decided to present this with an example building model, a special concentric brace frame system that will cover various features that we'll be using for the modeling, analysis, and design of a building. And the stages are listed here. You can see they are primarily comprises of these. For the object-based modeling, we need the definitions, and then we use the definitions like the properties, etc., to model the structure and its members. And then we'll make assignments like properties, loads, hinges, etc. Then we also going to perform a nonlinear analysis, which we will discuss in the model. We have the next stage is analysis, and then its outputs. We'll review them. And then if needed, we'll iterate, and then we'll perform the design of the members. If members are not satisfying the design checks, then we will come back to update the model with new properties, change properties. Right. So this entire process is the basis how we are going to use the program, and this is the workflow. So the definitions and modeling of steel structures, we have ready components like beams, columns, braces, truss elements from a library, standard library from various regions of the world and country-based. Section properties are available for you to easily import and use it in your model. And then there is an auto select option for you to do the preliminary analysis before entering into the final analysis and design of the model. So auto select is going to help you create greatly in that aspect for the preliminary design. And then we have special panel zone modeling for advanced analysis. So these are the basic things that you require in the definitions and for modeling. And then we are going to analyze the structure. We have a comprehensive and powerful analysis tools, like starting from the loading, we have the automated seismic loading, wind loading, based on various codes, international codes, including Indian codes. And then for geometric nonlinearity, we have p-delta analysis. And for material nonlinearity, we can consider in the analysis, the load case we'll set up. We will see that in an example shortly. And then we can perform dynamic analysis. Real-time earthquake data can be an input, and then you can perform the analysis to get the responses for various uh, inputs of time histories. So dynamic analysis possible. And then construction sequence, if needed, that can also be performed. So it covers all the required analysis tools. And then finally, for the specific steel design, and which also comprises of composite design, we have integrated code-based design readily available for those needs. Right. And finally, we have output, and also we can prepare uh, the detailing or detailed drawings, which is inbuilt with the program. And you also have the interoperability with CAD, Revit, or BIM integration. So the program is fully capable of handling all these requirements. Right. We will discuss some of the features, and then we will enter into the example model. So we have standard importable section properties for the frames, beams, columns, braces, etc. And then standard shell sections for defining the floor slab, walls, etc. We also have this special section designer in case you want to define an arbitrary geometry, like for example, a star column. And you can see that in the image, and it can be a composite. And you just need to prepare the geometry. Program takes care of the rest, the property calculations, etc. It can be used in the advanced analysis seamlessly. So section design is going to help you a lot in built-up sections, especially, right, which are not standard. So we have this feature. Then for the analysis, we have the p-delta analysis that takes care of the global and local uh, bending of the frames. So the program implementation for various codes. So for Indian code, to be specific, it is recommended that we do the p-delta analysis and then perform the design. So the effect length factor that is to be captured is then set to 1. So the second order moments are captured in the analysis itself. So p-delta. And then we have the panel zone modeling. Although we will be discussing SCBF, maybe in future that we will discuss the panel zones in detail. But you can see the panel zone, the beam column for the SMF type structures. So shear deformations can be accurately modeled and the response can be captured. The program has this feature, automated as well as user specified, also available. And then we have the auto select properties, obviously for the preliminary design, can do this, and you can also use it for optimization. And then we'll be using groups. The group is another feature where it is going to help us in the modeling itself by selecting objects by groups. For example, we want to assign the loads or change properties. So groups will, because we have typical members in the steel structures, like all the moment testing frames, all the secondary beams, like that you can group and then use them for all editing, assignment, etc. And you can also use to get section cuts. And the important thing here is in the steel building would be the intent to share the same design. Like for example, if you have a particular floor level where you can have auto select list program would have optimized, then each member can be slightly different from the other. Then we can group them and ask the program to consider the largest one for all members in that group. So this one will be greatly helpful. It will be more practical in the steel design during optimization. and it will be also used in getting the outputs. Now, code-specific design, we have various features. So program will calculate the demand capacity ratios, stress checks, which involving various calculations, parameters specifically like bit length factors, unsupported length factors, right? So these are all taken care by the program, and the design can be iterative and used in the optimization. And we have the two ways of doing this. One is applying a specific section property to the frames and then check the capacity. Obviously, the demand capacity ratio based on the equation will be reported. And then the design capability is optimization, basically that an auto select list is applied and then program will uh, iterate the analysis and design until these sections are matched. Right? You'll get enough information on that. We will demonstrate it shortly in the example. So the analysis and design section is the final one that we need to match. So program allows you to change the section with the current analysis and check the capacities quickly. But at the end, you will have the sections match. That is very much important. We will see that in the example. And then for design, we have various information to be fed. One is the design load combination, which can be defined by the user, or automated load combinations can be generated by the program itself. Right. For IS 800, the standard that is shown, specific design combination will be numbered and generated. So we can have you can define your combination using the scale factor specified. If it is program generated, then these factors are automatically incorporated based on the code selected. Then you can also involve notional loads, multi-value combinations like advanced analysis, response spectrum analysis, time history, etc., envelope or multi-step results. The program can handle all of these. And it also has the live load reduction. The default, you can control that based on the code, or you can specify it as a user-defined reduction factor. So all of this are coming into the design stage. And whatever you see from the analysis forces will be there, but for the design of the members, program will involve all this, and you'll get the final design forces that you will see in the output, which may not match the analysis forces. So section classification is the main start with the steel design. So program classifies this as for the 800 code listed here, class 1, 2, 3. Class 4 is not handled by the program. And then the L factor, which is the unsupported length factor, is automatically obtained by the program from the model itself. So you don't have to specify unless there is a need to, but you have options to overwrite, and you can see the determination priority, which program uses. Any overrides specified by the user, that will be the highest priority. And the precise basing definitions you can make, like lateral bracings at specific points or continuously for a beam, then program can recognize that from the lateral bracings. If specified, that will be used, or by default, the lowest priority is the automatic calculation from the connectivity of the members. So length factors will be obtained based on that. And effective length factors, so K1 and K2, K1 is non-sway and K2 is sway. So the program calculates both and uses it as per the design preferences. When P delta is done, then K K2 value will be set to unity. Obviously, these factors can be uh, overwritten on member by member basis if needed. Other than that, we also have the seismic design provisions based on AS800 covered. So frame systems, SMF and OMF, SMF and SCBF. We are going to discuss SCBF here. Concentrically placed frames, the ductile one. So the relevant clauses from the code are implemented, and it also checks as per the framing system selected for the design in the design preferences. It also checks for the joint design, and it reports these outputs. For example, weak column, strong column, sorry, weak beam, strong column for the special moment testing frame will be reported. And then panel zone, if needed, it can design the doubler plates and it will report the thickness, or if needed, the flange modeled as plates, the required area, the continuity plate can be designed and reported by the program, right, for SMF. And then it also reports the connection forces. And one last thing is how to model these members. Do not break it. Our recommended way is to model it as a single element. So the effects of breaking will affect the unbraced length, K factor, and CM factor, which affect the design as well. So one need to be aware of this information. And then lastly, we have the overrides for various parameters. And if anything is overwritten, that takes the priority. Otherwise, the default program determination of the parameters will be used, right? So overwritten values are not lost when the model is unlocked. So if you unlock and design the members, these overwritten values stays unless you change it to program default. That will be used. All right. Now let's jump to an example, and then we will see the various features. And I'm going to quickly do a couple of iterations so that gives you a practical usage of the program. We'll create a new model based on Indian region. You'll use a four-story building configuration with 8-meter span, and then 3 spans in X and Y direction, a symmetric building to demonstrate. I think it should be sufficient, and I will use the grid-only option so that rest of the things will be completely from scratch. All right. So for those who are new to this, you'll have the working windows. One window will be active, and you can switch the views as needed. You can add more windows, etc. So these things are basics, and we'll be using the Model Explorer this time to help us a lot in this deal. building analysis and design. Now let's right away start. Let me save this once. All right. Now let me start with the material property. So the default Fe345 is available, which I'm going to use, or you can add new material directly from here, but let's use Fe345. And then next, section properties, start defining the frame sections. We will import properties. Let's say I section for the for the beams, moment testing frames, as well as the secondary. Use ISMB 300 to 500 for the beams. And then let us quickly define some column section properties so that we can use it. This time I will use add new property just to demonstrate. Then you might need some higher sections. I will name it as C600. It will be an I section, depth 600, width 300, 20, flange thickness 16 mm, web thickness 320. Right. We'll add a copy of this. One more, a few. This is how you create this. 25 mm thick and 18 mm thick. Let's add one more copy. This time it will be C650. C700. And one more last 750, just to have enough sections for the iterations during the optimization. That's all. So these are the column sections, beams. One more last one for the braces, which we can define it as a pipe section. Can import, but I'm using a user-defined section. It has P 200 by 8, 200 mm, 8 mm. All right. So these are the sections available in the model database, but we'll be using auto select list for the beams and then for the columns. For the beams, we have a predefined auto select list. You can also start your own. I'm simply converting this to user, and then I'm going to update this. For the composite beams, I can have up to 300 to 350. Up to. And the starting section for the analysis will be the median section by area. It's the default one. You can also set a particular section if you want to start from there. And then for lateral beams, convert to user. We'll remove this. Lateral beams, we can have 300 to 500. And then columns, convert this to these sections. All right. That's all in the definitions. Next, the load patterns. We have the dead and live as default, readily available for us. We will add EQX as seismic based on the code. Auto lateral load. One more for the Y direction. Let us have the next direction. Let's say it's in zone 4. And the time period, let's say it is 0.3. And since it is SCBF, we can put response reduction factor for 4.5. Same goes for Y. Next, the mass source for the seismic will use specified dead 100%, live 0.25%. Okay. Now let's create the model. Go for the story one, and then I'll start creating this. So one more section property that is for the deck section. So now we can model the shells, but for steel, we have this specifically deck sections, which can handle the filled deck, unfilled, or solid slab for the resemblance. This way, program can recognize the composite possibility and recognizes the members, specifically the secondary beams, as composite by default. I'll show you that. Now we'll use a M30 concrete material and 345 deck material, standard, or the default section properties I'm going to use. And these properties will be utilized in the composite design. And the shear studs uses these properties. All right. So the default deck section I'm going to use for this. Let us start with the drawing of columns. Quick draw columns. You can see the list of section properties. So we'll use A. The A suffix is for identification of auto select as a naming convention. So use that column. And I will make a selection window. Columns will be created. Then I will select these columns and change its orientation by changing the local axis to 90 degrees. Next, we draw the beams. Autolateral beam. And then we draw the deck, just defined, deck 1, and the orientation, change it to 90 degrees. And then lastly, we will define the secondary beams. Composite number of beams 3 in X direction. That's all I have to do to create this. The last thing we'll model is the brace after replicating this to other stories. Let's select this story, story 1, and then we'll replicate this 2, 3, and 4. Right. Now, I'll change the control type to all stories. This is to define various groups and assigning members to these groups. Now let's select all the columns, like using the object type, columns. Then we'll use assign objects to group. Currently the list is empty. We can create them quickly from here, which is also available under the define groups. We'll add walls. Let's add one more group, beams. Composite beams. One more for braces. Now assigning all these MRF calls, add to group. And then I'll select all these secondary beams. We'll remove the joins from this, and then go to add to group. We'll select all the beams once again, and deselect the composites from that. So these will be moment resting frame beams. We'll apply these members to this group, right? The last one for the modeling will be the braces. I'm switching to elevation 1, and I can quickly use quick draw braces. We'll use a particular section for this. So this is moment released, pinned. Right. I'm keeping it all story. So one click at a story will generate this. Now switching to elevation 4. We do this again. And then A and D. All right. This can also be auto select list. So one important thing for the bracing is I'm assuming that these braces are not connected at the midpoint. So in the modeling, we need to select this and specify assign frame auto mesh option to no auto mesh. Right. The last thing would be the loading for the floors. I'm going to select all the floor objects just for demonstration. So I'm using the same uniform load as dead load, say equal per meter square in the gravity direction, then set previous selection, then live load, say 2.5, right. All right. Now this is the usual uh, gravity and lateral loads that a structure is subjected to, and we'll be designing this now. And for that, we have to run the analysis. Let's go ahead and run the analysis. I wanted to show you more things in the display. You can get to see the frame sections because members are auto select. As I said, the section selected for the analysis is a median in the list based on area. You can see the section name and it starts. Now let's perform the analysis. And ensure everything is okay. The deformation for the gravity looks fine. This is for lateral, X and Y, everything looks fine, right? Deformation is about 10 mm at the top level. Now we have used the default settings when you start with the program, especially for the end length offsets. Let us also see the time period. It is 0.58. 0.58. Building is symmetric. It's expected. I'll unlock the model. I'll select all the frames, beams and columns, and assign them with frame end length offsets. By default, it is automatic from connectivity, and the rigid zone factor is 0. That means the flexibility is from the end point of that member. It connects with the column, right? So we will set this rigid zone, this beam column junction, assuming that it is rigid. And over and above this, you can also assign panel zones, which I'm not doing in this presentation. But rigid zone, you can see in the graphical. Then now we perform the analysis once again. the lateral. Now it is 9 mm. It's reduced as expected because it's less flexible. Time period is 0.57. Right. Now till here, it's the usual analysis that we do, and you can get the frame forces and other things as usual, which I'm skipping, and straight away proceeding to the design of these members. So under the steel frame design, since we are allowing the optimization through the auto select list, we have options to set displacement targets. So are based on time periods. So you can set the time periods and ask the program to do the optimization. So the program can change the section properties and it will run the analysis and design to match that requirement. But I'm only interested in this. I'm okay with these displacement targets right now. I'm skipping those, and then I can enter into the preference. And here you have preferences, specifically the frame type for which you are going to design based on the seismic clause will apply. So this will be SCBF, and it will be based on zone 4. You need to select, and other information based on the code, like whether you want to ignore the seismic code, ignore special loads, right? And the limits for the deflections to be checked. All of this are listed here. I'm accepting these, and then setting a demand capacity ratio, which is the final DCR that will be displayed for each member. If it is greater than 0.95, the default value, then it will be in red color, means it is failure. You can set it to 1 or any other ratio that you want. Right. Now we can perform the design and the load combinations. I'm leaving to the program to generate for me, and then I'm going to perform this start design check. And once the design is performed, it gives you this information. Analysis and design section differ for 160 frames. Do you want to create the analysis and design? That means this section property I showed you here in this left window, that is being replaced with the optimal section in the design. And this is a message that tells you about that. Let's reiterate. That means the selected section for the design will be used in this iteration of the analysis. Let's do this. Now there are 32 sections. It's okay. There are 6 more. Let's do one more iteration. So there are 18 steel frames and auto select sections failed. You want to select them. Let me check. Yeah, these are the beams. The same message, but you can see these are the moment resting same beams. These 500 is not sufficient, but we will find out why. Now at this stage, what you can do, first let us review the reported design output. You can see in color codes, but we can get the DCR values, display design info. You can see the ratios here. Columns are okay. In this frame, this is crossing point, 0.95 utilization limit. That's why it is showing in red of the frame. And then these beams are failing because it is exceeding 1.0 to 1.06, marginally exceeding. A different section would help. But what happens when you right click on that, you have to ensure that the analysis section and design section will matched, which you can also get from here. Design, steel frame design, you can verify analysis with design section. All are matching. This is good enough. Now the exceeding ratios can be addressed by specifying a new section. Now you can see for the column, it has selected the lower section for the corner columns, and then near the braces, I can see it is selected C700 section as per the demand, and the interior one 650. Right. So you can see the variations there, but the optimization is happening with that. Right. Now let us see a plan view. Right. Now we can see the periphery beams using 450, 350, and 450, 500. Right. So these variations are there. So this is where the groups will help us. So program will try to get the maximum one from that list of members. So I'll use moment resisting frames. Then I'll perform the design once again. See how it works. Let me try one more time. I'm trying to find number of beams. Okay. Yeah. Let's perform the analysis one more time. Let me analyze with this one. Yeah. The message should happen. Okay. That is something that is not happening, but it should happen. Right. So during the optimization, once all the members are matched with the analysis and design, so right now it is matching. What you can do, you can make the auto select section null typically for any model, so that so these sections are freezed for further. So select all the objects, all the beams and frames, and sorry, beams and columns, and then we will assign make auto select null, right? And then now you see these sections are replaced with the actual final property selected for this. So this way, there will be no further iterations, even if you unlock the model and design. So this is how you finalize, or you can also use chain section design to select the members and specify a particular section for the selected members, and then finalize the design, right? Now, we can increase this section slightly and make them pass, but I'm continuing with that to save some time. So next item will be the nonlinear analysis that you will have to perform to find out whether the members are yielding or the behavior or yielding of members are as expected, right? So for that, we're going to define nonlinear static load cases. Will be basically a pushover analysis for the limits of uh, maximum drift allowed for this structure. So this is done after your after your design is finalized. Now we are assuming that the design is final, and then we are defining these combinations here. Gravity, this is to apply the gravity loads, and the important thing is zero initial conditions. You have dead and live, 100%. The loads are applied full, no further changes on this. Next, we will add EQX, but nonlinear. Continue from the state of the nonlinear case gravity, and the loads applied will be a load pattern UX. It uses a pattern, but it will be based on the displacement that we will monitor. So the building height is 12 meters. Maximum drift ratio is 0.004. So we can see 48 mm you're getting. So we will study if for the 48 mm deformation, whether the members are yielding or not. So this will be in X direction at the topmost story level, any joint. And then the results you can ask for final state or multiple state. We will create a copy of this for Y direction. Displacement control, again, the same 48. U2 represents Y. We'll have this. All right. I'll unlock the model and then select object by groups. Now you have the option here on the Model Explorer to quickly access. You can see moment resting beams. You can select them and assign them with nonlinear hinges. Now these hinges will give you the moment rotation or specified uh, nonlinearity that is to be monitored. So we will be assigning moment hinges for the beams, PMM hinges for the columns, and axial hinge for the braces. So the hinges you need to define, but I'm going to use ASC 41 or the FEMA-based hinges, user-defined and auto hinge property. I will show the hinge definition shortly. Let me add this. So for beams at two ends, 0, let's select, let's see, there are several things to be used for the definition, but I'm keeping it simple. So it is M3, the major bending moment. Hinge will be monitored for that. Then one more. It's okay. You will see these beams are applied with these hinges. Next, we'll select the columns, assign them hinges. 0. Steel columns will be PM2, M3, 0 and 1. Columns. Select the braces. These are important because this is SCBF system. We will assign them with a hinge that would be at mid, an axial hinge. Right. Once these are assigned, and we can go back and see this definition under the section properties, frame, wall, hinges. Can enable the show generated props to be for each beam. We'll have 1 and 2 for both ends. We see the beam hinge. This is based on the code. When you define, you can define, take the control and define completely. Basically, this is the post deformation or the moment rotation that has been defined here, right? So program is capable of doing the performance-based design for that requirement. Performance criteria can be set, acceptance criteria using this, which can also be displayed here. But we will skip that, but let's focus only on this part. When this is the yielding point and any member yields beyond this point will be displayed graphically, as well as other outputs are also available for that information in a tabular format. All right. So beam, go for a column, any column. B point is the yielding point and plateauing, and then failure. Similarly for the brace, steel brace, you can see in tension, it has a capacity. In compression, it has very small capacity. You can see the capacity is calculated automatically. All right. So that's the definition. Now we can perform the analysis. We need another 5 to 10 minutes, and then we will close this. And this is complete. Now let's go to deformed shape. We'll check the nonlinear EQX. So for each step, we asked for multiple steps. So output you can see for 9 mm. It's okay. So you can see the braces starting to yield. So it's a 13 step, the last step. So you can see the UX deformation is 48. Right. Although the linear static analysis is safe, you can see with this maximum displacement of the structure, that is also very small displacement, about 50 mm. It's not much. For that, you can see the braces are yielding. I'm selecting this brace, and then you have output that can give you the hinge result. And you can see it is buckling in compression. You can see the compression region. In axial force, this is losing its capacity. You can also yield in tension on the other side, but we push the structure and we are studying only this, and we see this one is not yielding yet. Right. And the same you can find for y direction also. And since it is symmetry, you can see a similar failure of bracings. But you can also see the frames, beams and columns are not yielding. It's a good sign. Only the braces is what expected in this system. You have various other outputs based on the analysis selected, like pushover curve. You can see the ratcheting of the base shear versus mounted displacement diagram that reports that yielding along the way. Then many other things beyond that would be for the performance-based design, which I'm not discussing. But you can see the nonlinear behavior of the members, which is designed perfectly as using a linear static analysis. This can be studied here. We can extend this further for a time history analysis that will have the full lateral sway, positive and negative, and then members can fail differently. I'm stopping this at this stage. And then one last thing I want to show you in this model is the design of composite beams. Now, program by default recognizes these members for the design, steel frame design, and these beams, along with the deck property slab, it can recognize correctly as a composite beam design procedure can be applied to this. By default, it does that. Then you also have the option to override the frame design procedure. If you want to design these secondary beams as steel members, you can do that. But for the sake of demonstration, I'm going to perform the composite beam design. And you can see the design code, IS 11384, recently introduced in this program. And we will set various preferences. For example, for the beam, shear studs, so minimum PCC and maximum PCC, cambers, deflection checks, so vibration checks. Vibration checks will be based on DG11, Design Guide 11 of ASC 360. So prices, we don't want to optimize this. The factors associated with various safety factors. used. So with this basic and the default definition, if I go to composite beam design, and again, I'm going to leave it to the program to generate the combinations. Start this. Oh, selected this beam. Let's see. Design composite beam. Start design check. Yeah. Similar to the steel, it also can optimize by selecting the appropriate section required. Now you can see this interface is interactive. I can see majorly the strength checks and the demand capacity ratio is listed in the last column. So easily you can identify, so whichever is giving the largest ratio will be displayed as for the selected member. You can also see for alternatives. So in that list, 300, 325 is also possible, but 350 is sufficient because you can also check why they are not okay. But you can also interactively change some input values like camber, percentage of composite from here. Then it can do this, update the design, and you can get the ratios quickly from here. So the second half is the serviceability check. It's also performed, and you can see it requires 25 mm camber. So the graphical window, it shows that 36 shear studs and a camber of 25 mm is needed to handle the design. Right now, the detailed design you can get from here, report. So the program can identify the deck and how the ribs are perpendicular. You can see these are perpendicular to the deck. Perpendicular to the beam. Then it calculates the shear stud capacity and all other outputs related for the checks. Section properties used, composite section properties, partial, full. So everything is detailed here, including the vibration frequency values. Now you can see that here, peak acceleration is 0.002, limit is 0.005, and the ratio is 0.3, then it is safe. So the same way, every design check is reported as a TCR value here. So whichever is maximum, that is reported here for quick identifying. So that's the composite design. Just an overview. That once you start using it, there might be queries on these. Then please contact us, where we can discuss it further. Right. So one more example, last one, just for demonstrating, that is for composite columns. We have a model ready for that. So it's a typical office kind of a building where we used the composite columns. Select C350, 350. So basically, you have the steel composites that can be designed at the steel filled tubes, square and circular, and encased dissection, rectangular and circular. I see this. You can see it's a tube filled with M25 material. That's the definition. Then if I perform the analysis, no optimization, then directly the section are applied to these members. So we'll get the listen directly. Is composite column design. So we have the preferences for IS 11384. I'm accepting the default and performing the design right away. might take a while. I will cancel this and we'll review one column output. So similar to this frame design, you can see into the details. Basically, again, it reports a DCR. Very much similar to the steel frame design, but the composite design of this is now being done in the ETABS. Okay, so that's all I have for today. Hope it was informative. Let me quickly see uh, any questions from the participants, and then I'll try to answer. Okay. Yeah, I think why pin support but not fixed. Yeah, uh, you can decide on the support condition, but for this one, I used pinned. Yeah, the braces are helping in the lateral, controlling the lateral deformations. Yeah, what is SMF and SCBF? Okay, we have ductile detailing for. Okay, for ductile special or ductile moment resting frames, we have other checks to be done. Uh, so those are taken care by the program, but you can always do that. But typically, the SMF will be requiring higher sections because there are no bracings. So SCBF, we have the bracings, uh, kind of a dual. So it is. So code is guiding you. So all the relevant design checks are based on those. It's incorporated in the program. So partial composite, I think there is a question on the partial composite. Yeah, program um, will iterate during the design process how much from the lowest percentage or the minimum percentage as per the code. Then when it achieves the partial composite properties are used accordingly in the design. Because but you should understand that these all of these are in the design stage, not actually modeling the analysis. So you need to review the design procedure for more information on this. Yeah, I think SAP 2000 does not have this design feature, so we'll have to use ETABS for this. Yeah, I think overrides are available for changing the frame type. You can do the override member by member basis. That is the question about when to use SCBF or SMF. So plus, okay. So for the from the pushover analysis, no plastic hinges are getting formed. How to get the pushover curve? No, if it is not forming, it's not forming. But you need to review the hinge definitions. Maybe the properties for the definitions are not correctly modeled. But if it is not forming, then it is not. It is linear. The behavior is linear. We will provide the recorded session of this. So there are enough tutorials to start ETABS learning. You can visit our website or our YouTube channel to get more recorded sessions of these introductory and special webinars on special topics. You can get them. Yeah, braces are taking care of the lateral forces, and we are defining this as moment resisting frames. That's the dual system usually we make, but you can also make the beams composite. Yes, you can do that. Okay, buckling restrained uh, braces are also available to define in the program as a frame definition. You can do that. So rigid zone factor is applied to account for that beam column. Although we are using the finite element, it's a line element, right? That joint becomes more rigid in that zone. So that zone factor is being specified as 1 for steel. In case of RCC, this is in general specified as zero 0.5. Yeah, the braces are not supposed to get connected for this model. That's why there's no mesh, no auto mesh. If you want, then simply leave it to the default assignment, mesh assignment to the frames. Then it will get connected, and then distribution of forces can you can see after the analysis. Yeah, I think you need some experience in the steel to start with. But for anyone new, then you can also use list of sections, and then you will try to find out the optimal section, leave it to the program, and then you can maybe in a couple of projects you will understand the sizes required for a particular type of system. That's the way to learn it. Yeah, we will discuss on the 25% requirement for the dual system will be in another Q&A or another webinar if possible. We will provide a recording session. I think for other questions, if I'm unable to answer, we will provide some answers through the Q&A session. Hope that would cover the rest of the queries. But I think we are running out of time already. So I will close the session. I hope it was helpful. Thank you all for your participation. I hope it was helpful to start using the ETABS for the steel. Yeah. Thank you all once again. Meet you in another session.